All right, good morning, everyone. So today we're going to talk about a different way of ensembling. So last time we talked about ensembling with methods that were trained in parallel. So you trained a bunch of predictors individually, and then you figure out a way of putting them together to give you a better result. And we also learned about decision trees and how you can put those together to create random forests. And today we're going to talk about boosting, where you sequentially train a number of different models, train one and then train another to improve the first and so on, and then you put them together to do better. Okay, so again, the main idea here is train them sequentially. That's what gives us boosting. The picture down here shows start with your original data set, train your model just like we always do. Then you see how good the performance is, see where you made some errors. And then typically what you do is you do something like on the samples that have the error, you weight them higher when you train your next model. And then you see how that performed. Maybe it made some different errors. You weight those higher than the other ones. You train another model and so on. Once you have all these trained models, you figure out some way of weighting them together to get your final model. So there's a number of these methods. We're going to cover 3 of them. First is adaptive boosting. This is back from the mid-90s. And then gradient boosting around 2000. And then extreme gradient boosting, or Xgboost, which is quite a famous approach these days. And as you'll see, they get more complex as we go. They kind of, one builds on the other, which builds on the other. Okay, so let's start with the simplest one, add a boost. So our goal is to train an ensemble of predictors. There's going to be a total of capital M of them. We'll call each predictor FM. And this is what we do. We go in this for loop over the little m. So we train predictor FM to minimize some weighted loss. So here you can see is the loss we would typically use. And then we have these weights. And as you can see, the weights depend on the step m in the for loop as well as the sample index I. So some samples will be weighted differently than others. And so once you have this loss, you can train a predictor sort of like how we typically do. You just have to change a few equations to account for this weight. It's not really too difficult. We won't even get into those details. Just assume you can train that predictor. Once you have that predictor trained, as we'll see, you can evaluate it, and then you adjust the weights on all the samples for the next round. And then you go and you train another predictor, and so on and so on. When you're all done training all your capital M different predictors, you put them together by weighting them by these weights alpha. We, of course, want to learn these weights as well. And then we get this capital F, which we'll refer to as the boosted predictor. And when we start out in this simplest case, we're going to focus on binary classifiers, where our predictor puts out only 1 and -1. So there's hard predictions. And there are versions of add a boost for regression, for non-binary classification, but for us, it's enough to talk about this because this will allow us to extend to gradient boosting and so on. Okay, so that's the objective. All right, so how exactly do we do this? So as usual, we have our training data, feature vectors xi, targets yi. We will assume that our targets are also plus -1. The base classifiers, we will restrict them to put out plus -1. And so this is how we do it in our for loop. So let's call the step m boosted classifier f little m x. So if you remember, we have the overall boosted classifier at the very end being F capital M. But you could imagine that along the way, we can have a partial sum over some, index M, and that will give us this guy. Okay? And so we can write that as the boosted classifier at step M minus 1 plus the new term in that sum to get us the boosted classifier at step M. So what we're going to do is we're going to just build up this guy iteration by iteration, and by the time we get to the end of our for loop, this will be F capital M, and that will be the final thing we're trying to design. All right, so does that make sense? Okay. So, and we're going to initialize F0 at 0. So, that makes sense. So basically at step 1, this is 0, so we're just going to have this. All right. So what we do in our for loop for each little m, we're going to design a positive weight alpha m. These are the weights, again, that are here. Design a positive weight alpha m and a classification function f of m so that f, the boosted classifier fm, minimizes the exponential loss. So this exponential loss is something that you haven't seen before, except actually you saw it on the midterm. But if you think about it, it kind of makes sense. So remember that we have a classification problem. So we want that the signs of these capital FMs are correct, right? So if the sign of y and the sign of FM match, whether it's positive or negative, the product will be positive, and then so negative of that product will be negative, and this e term will be less than 1. On the other hand, if you get the sign wrong in FM, then the exponential will have a positive, and it will be greater than 1. And in fact, if FM is the wrong size, the larger it is, the worse the penalty. And if FM is the correct sign, then the larger it is, the smaller the penalty. So it's kind of similar to what we saw with Z, our score, before when we talked about classification. Here, the little f is plus minus 1, remember, but the alphas are real numbers, so the capital F's are also going to be real numbers. They won't be restricted to 1 and minus 1. Okay, so we want basically f to be as large as possible, but matching the sign of yi when we put in xi. Okay, so that's our loss function, and this loss is really easy to work with, just because exponentials are really easy to work with, and that's really why it's being used here. As you know, it's very easy to take a gradient of an exponential, take a derivative of an exponential. Okay, so let's see how it goes then. We kind of set up what we want to do, and as we'll see, it's actually possible to do this design, to find the optimal alpha m and fm. Okay, so to start, we have our loss. We also have our equation for capital FM. Let's plug that equation into the loss. So then we get this. So in the exponential, we have the previous boosted classifier, which we have already designed, and then we have this new addition, which we are trying to design the alpha and the f. Okay, so because we have a sum in the exponent, we can rewrite this as a product of the first term and a product of the second term. And of course, this first term, we're not designing this. This is given because we have already designed the previous f. And we are going to think of this as a weight. And we're going to call it WMI. So this is the weight for the mth stage and the ith sample. And like we just discussed, if our previous boosted classifier is making a correct decision, we will use a small weight. If our previous boosted classifier is making a wrong decision, then this will be a large weight on that sample. So, if we mess up the next time for a classifier, we're going to say, don't mess up on those samples. You learned your lesson. Okay, and then this is the remaining term that has actually the parameters we're trying to design. So in an effort to better isolate those parameters and see how we can do that design, the first thing we're going to do is we're going to split the sum into two sums. The first is going to be a sum over the samples I, for which our little fm is making the correct decision, and then another sum over the samples I, for which it's making an incorrect decision. And now there's a simplification, because when we make that correct decision, since f and y are both plus or minus 1, when we make that correct decision, their product is 1, and therefore this term in the exponential we can just replace with a 1, and then we get this. And in this other sum, when they don't match, that means that their product is minus 1. Then again, we can replace this with a minus 1, and then that reduces to e to the power alpha m. So essentially now what we've done is we've transferred f. The only place f appears is in these summations. But it's appearing in two summations. Maybe we can simplify this so that it appears only in one summation. That will make it easier to deal with. And the answer is yes. So what we can do is we can complete the first sum. So right now it's incomplete because it only has the samples for a correct decision. Let's complete it by adding to it all the samples for the incorrect decision. So those are going to be these samples, but with this term. And once we add those, this just becomes a nice sum over all the samples, so there's no more f. But because we added, some terms here, we have to subtract them again. And in fact, that's what this is. So this is all the terms that we added to complete that first sum. So we have to subtract them here. And then what was in the second sum, this is just this first term. Okay. Is everybody with me so far? So what we have succeeded in doing is isolating f, so the only place it appears is here, and okay, the alphas appear here, but as we'll see, the alphas are not so difficult to deal with. Okay, so again, this is our loss. At time m, we want to design f and alpha m that minimize that loss. So if we just say, well, let's design the f that minimizes that loss, notice that this term is positive. This is because alpha is greater than 0, so the first term is greater than 1, and the second term is less than 1, and so greater than 1 minus something less than 1 is still greater than 0. So this is positive, so if I want to minimize this overall thing over f, I can just focus on minimizing this. And it's kind of intuitive what we're doing. We're minimizing the weighted misclassification loss. Okay, so imagine all the weights were 1, which is what happens in the first iteration. If those are all 1, all we're doing is we're minimizing the number of incorrect decisions we make. That would be just, minimizing classification error. But now in this framework, we have weighted some of the samples differently, and so we're minimizing the weighted classification loss. Another way we can write this, if you don't like writing this in the sum, you can also write it like this, where you sum over all the samples. You have your weights, and then you have an indicator function that takes on the value 1 when its argument is true. So when we make a mistake, this turns into 1. When we don't make a mistake, this turns into 0. And of course, if that term is 0 for a particular I, then it doesn't appear in the sum, and that's why you can see it's equivalent to this. So this is another way of writing it that might make a little bit more sense. In any case, this is something that, again, we can do using a standard method. So if you want to do this with logistic regression, you just have to change your cost function a little bit to put in these weights, but you can do a derivation and figure out how to minimize that. At step 1, we're going to use weights that are all equal to 1. And so the first classifier we design is just our standard classification error minimizing classifier, but at steps greater than 1, we have these weights that could deviate from 1. And so essentially what we're doing is we're designing our new classifier to try to make up for the errors made by our previous boosted classifier. Okay. Everybody with me so far? Okay, so we've figured out how to design F. Now we just have to design these alphas. So it turns out that this is pretty easy. Using the same method that we've been using all term, you just set the gradient of the loss with respect to alpha to 0, or it's just a derivative because alpha is just a scalar. You just set it to 0 and solve for alpha. And you can see because the alphas just appear in these exponentials, the derivative is going to be pretty easy to compute. So essentially what happens when you set it to 0 and solve for alpha, you get alpha of this form, where these epsilons are a weighted error rate. Okay, so the numerator sums over all the i's where you made a sample times the weights, and the denominator sums over all the i's times the weights. So basically, it went from a total number of weighted errors to a weighted error rate, because you're normalizing by this. Okay, so that's pretty much it. So in summary, to train Xgboost, you initialize the very first weights at 1, and then you have a for loop where at each little m you do the following. First you design your classifier, then you compute this weighted error rate. Based on that weighted error rate, you compute alpha. Now you know how to add f and alpha to your previous boosted classifier to get your current boosted classifier. Then you can evaluate your current boosted classifier, and you can see what the new weights will be. And then basically you have finished that iteration and you go back and you do this over again. And when you're all done, after little m becomes capital M, then we finally have our boosted classifier and we can use it for prediction. All right. So, is this making sense? Let's see a little visualization of this. Oh, actually, let's talk about the implementation in Sklearn. So this is done in Xgboost classifier, or actually there's a regression version, Xgboost regressor. And by default, the method that it uses for the predictors little f are decision trees, and it uses 50 of them, so for a loop with 50 iterations. But actually these are decision trees with depth 1, sometimes called decision stumps. So they're very simple, very easy to train, but when you have 50 of them, they can really get more sophisticated because they build on the previous ones. So here's just a little illustration for what happens if you had 3 of them. So we have data set, 2 feature dimensions, pluses and minuses. You can see the binary data. So at the very first iteration, let's say that we train our decision stump, which basically means just partitioning with a horizontal or vertical boundary, right? That's all it's going to do. It's going to pick either there or there somewhere. So let's say it picked this one. So now you can see that it made correct decisions on these 2, but it made incorrect decisions on these 3. So for the next iteration, it's going to weight these larger. And so that is illustrated here by the fact that the pluses are bigger and all the other samples have gotten smaller. They have small weights. Actually, it's going to down weight these because it made correct decisions. The weight's going to be less than 1. So in the second iteration, we want to minimize the weighted error. So now essentially we're counting these samples more than the others in that weighted error rate. So in order to minimize that, we want to make sure we are correct on those. So maybe we put a decision boundary here. And now you can see, good, all the pluses were correctly classified, but now these 3 minuses were incorrectly classified. So what's going to happen is these minuses are going to be weighted larger for the next iteration. So that's illustrated here by them getting bigger. These pluses are going to get smaller. And actually these pluses and these minuses are going to get even smaller because we made correct decisions on them. So now with the sizes of these pluses and minuses, you can see we really don't want to mess up on the minuses here. So maybe we'll put our decision boundary here this time. And so now we have our three little f's, and we haven't really talked about exactly about how these values, but maybe these are the alpha m's that came out of every stage. And essentially we just do a weighted average. We do 0.38 times this shape plus 0.58 times this shape plus 0.87 times this shape. And at the end of the day, we get this. And you can see that even though our individual weak learners were very simple, just decision stumps, just with three of them, we were able to make a very nice nonlinear classifier that is perfectly classifying all our training data. All right. So, any questions on this one? Okay. All right. Pretty cool method. So, gradient boosting, we can think of it as an extension of the previous method. So once again, we want to design the final boosted predictor to minimize a training loss of some form like this. But we want to be a bit more general. So as always, our training loss sums over our training data, and then we have a per sample loss non-script L that takes in the sample as well as the prediction that we make from the feature vector. And just as before, our boosted classifier is going to be a weighted sum of some alpha m's times fm's. A little bit different. So before fm was restricted to output plus or minus ones, now we're not going to be so strict. Maybe it puts out a real number, maybe it puts out 1 minus 1, maybe it puts out something else. We'll just describe the set of points it puts out by this script f. Some field, real, discrete, whatever. Also, the loss, we want to be more general. So when we did AdaBoost, we used exponential loss, and we used these FMs that put out plus minus ones. So now we're saying we want to use more general losses, and we want to design more general classifiers. So that's basically the idea, general L and F, but otherwise pretty similar to AdaBoost in spirit. Okay, so if we take this as our goal, you would then say, all right, so at the very first step, we want to train our FM to minimize our just usual loss. So, we know how to do that. We've studied many ways to do that. So once we're done with that, we're just going to assume alpha m is 1, or alpha 1 is 1, let's say, and we're just going to set our first boosted classifier at f1. Now in the next step, we want to take our previous boosted classifier, fm minus 1, and we want to add the product, alpha m, fm, to it. Okay, but how do we design that alpha m? So this is the alpha times alpha m, fm term. So it's going to be the argmin of this product, alpha m times fm. But as before, fm should be in field f. And of course, alpha m, we want to be positive. But how do we design them? Well, ideally, we would design them so that if I added them to my previous boosted classifier to get the current boosted classifier, then that guy would minimize the loss. That would be ideal. Okay. Does that make sense? So this is just fm. So if I could design the update so that the new FM minimized the loss, that's exactly what I want to do. I would be minimizing the loss at every step. Now, unfortunately, tackling this directly is too difficult. Don't know how to solve that problem. So the main idea behind gradient boosting, or one of the main ideas, is don't demand an exact minimization. Instead, settle for a gradient step. just move in the right direction. In other words, your next boosted classifier is your previous minus alpha m times the gradient of fm, the gradient of the loss at fm. So not a perfect minimization, just a gradient step. Okay. Is that making sense? Okay, but even this, there's a problem with it. The problem is that we want our FMs to output something in this field F. Maybe it's plus minus 1, maybe it's 1, 2, 3, whatever it is. And you can see that this should have the form of little f, or negative little f. But the problem is the gradient is not necessarily going to give you something in that field. So that's the issue. So this is what I describe here. Okay, so we're limited to updates of this form, where f should be in this field f, but this is what we are proposing to do in gradient boosting, and you can see this fm is basically now we're using for that the negative gradient of the loss, but how do we know that this is in that field? So if you look a little closer, what is the gradient of the loss? Well, you have the sum over all the samples, and then you have the gradient of the non-script loss with respect to this capital F term. Let's give that a name. We'll call it minus RMMI. But as you can see, this is not guaranteed to be in the field F. So, what gradient boosting? Yeah.
I don't know what you mean by in the field of F.
So like an example of a field is the set of real numbers is a field, the set of complex numbers is a field, the set 1 minus 1 is a finite field. And so we're saying the classifier must output things in a certain field. Like sometimes that field might be plus minus 1, sometimes it might be 0, 1, sometimes that might be 1, 2, 3, 4, sometimes it might be a real number if we're doing regression. We're trying to be general here, so we're not picking any one of those, but we're just noticing that there's some field F that is, we are restricting our base classifiers to output. Okay, and yeah, so if I just take the gradient of the loss, I'm going to get probably just some real number. It's not going to be within, let's say, a finite field. So that could be an issue that kind of spoils the whole idea of gradient boosting as going beyond this very specific problem that Xgboost solved. Okay, so what we're going to do is we're going to, again, make another sacrifice. We're just going to train F. We're going to make sure that it's in the field and be close to the negative gradient. So we're going to find, hopefully the closest F that outputs something in that field to the negative gradient. Okay, so exactly how we do that is we set up this quadratic cost. Okay, so this RMI is, remember that is the negative gradient. That's what we wish we could set FM to, but it's not going to be in the field F, so we settle for this quadratic. So we're just looking for the F that outputs things in the desired field that minimizes this quadratic cost. As close to that negative gradient as possible. Is that making sense? So we're using the gradient instead of doing the optimization exactly, but even the gradient is not going to satisfy our constraint, so we're going to satisfy our constraint by designing F as close to the gradient as possible, where close is measured in basically the L2 norm, the sum of the squares, Euclidean norm. Okay, so So we train F to do this. Tree search is a really nice, capable way where you could set up just about any cost you want, and then, as we know, you have to think about the different. When we train a tree, we think about, okay, which feature am I looking at right now? What is the threshold on that feature to minimize the cost? I do that for some subset of features, and then I move on. And it's very, you can use essentially any cost you want. It's not like you have to do a lot of crazy derivations and stuff. So tree search is super convenient for this kind of stuff. Okay. So let's assume with tree search, for example, we can train our classifier to minimize this objective. So now FM is trained. We have it. Then the next and last thing we have to do is we have to train the alpha M's. So for this, we're going to train it according to line search. In other words, we're going to just make like a grid of alphas, positive numbers. Actually, let's see. It maybe not even positive. I don't think it needs to be positive in this case. We're just going to find a grid of real numbers, and we're going to find the real number on that grid that minimizes our script L. So this is, again, the sum of the samples. This is the per sample cost, our target for the ith sample, and then this is what our new boosted classifier will be, for a particular alpha. So we'll just find the alpha that minimizes our overall loss. So we call that line search, just searching over a line. And once we know alpha and M, then it's very simple. We just update our boosted classifier as always. Okay, so this is the loop we do. We just go round and round this way, where at every step we compute the gradient to get the RIs, but then we design our tree, line search, boost, and so on. Okay. Is this making sense? Lots of equations today. Okay. Okay, so in terms of implementation, it turns out it helps to slow the process down a little bit by putting in some learning rate mu. To me, it's a little strange. You're going through all this effort to find exactly the best alpha, and then you're dividing it by, some number like 10. So, but that's what's done in the implementations. And so in sklearn, they have gradient boosting classifier, gradient boosting regressor. Both cases, they're using decision tree classifiers. They're using 100 of them. And these guys have depth 3. So not stumps, but not very deep either. Both cases. In both cases, they use mu as 0.1. Okay. Just the defaults, of course, you can change any of these parameters you like. Okay. So that's essentially how it works. Any questions? Let's just look at one example of output. This is a gradient boosting regressor problem. So there's this smooth line here. This is like the ground truth. So this is the actual function. Similar to way back in like the polynomial chapter, we said, let's come up with a synthetic data set where we came up with some polynomial line. And then from that, we added samples with Gaussian noise. That's what's happening here. There's some true function. Then you can see the samples or the dots they added maybe with zero mean Gaussian noise. And then those dots, that's the training set. And from those dots, we're hoping to learn the true function, although of course that's not going to be possible with finite number of dots. But anyway, this is how it works. So just as an example, if you did I think this is a regression tree. I think that's what RT means. Regression tree with max depth of 1, that would be pretty primitive. That would give you this line. If you do a regression tree of max depth of 3, that I think is, let's see. Well, maybe I got it wrong before. Okay, I think this is the depth of 3. Okay, so it's not bad, but it's still kind of rough. And then the max depth of 1 is this one, very primitive. Okay, now what if you, so this regression tree max depth of 3, that would kind of be like the first iteration of your gradient boosting. Because after that, you just keep adding another alpha M, FM, another one to try to improve. And so that's what's shown by these red lines. And as you can see with all these red lines, like things just keep improving. So they're basically plotting in this for loop as you go through the stages. And it looks like they have, I guess, I don't know if it's, could it be 2,000? Maybe it's 2,000, yeah. So they have many, and as you can see, what happens is as you add more and more and more, it looks like it's converging to something. It's converging to this dark red line. And the dark red line does a reasonable job of matching the ground truth function. It's of course not perfect, but the training data, as you can see, is pretty limited. So it's doing what it can with that training data. And there is a bias variance perspective, if you like. You can think of when you just have, a very simple predictor, early in the stage of this, that would be like high bias. With one predictor, you can't really, it's not sophisticated enough to come up with a good approximation to the line, but it's low variance. And as you get many of these predictors, you transition to a low bias, high variance regime. So, okay, so this is just an illustration. All right, so any questions on gradient boosting? All right. So this brings us to Xgboost. Basically, it's an evolution of a gradient boosting. So based on all those ideas, and it works extremely well. It wins a lot of machine learning contests, or that plus other tricks win those contests. And it's very easy to. You just run it. There are of course parameters you can tweak, but under the defaults, it usually does pretty well. Okay, so what is it doing different compared to gradient boosting? Well, rather than just looking at a gradient, it looks at a second order Taylor series approximation. So gradient would be first order. This is doing a second order. It also uses regularization. The regularization is used to try to design the trees better. We're going to talk about that. It has a sophisticated tree search. We won't be able to get into some of those details, and it has many parallelization and hardware acceleration tricks that help it to run faster, and I won't get into any of those details. But those are all the ingredients, so we'll talk about a couple of those. This is not part of Sklearn. It's not in Sklearn. It's in its own separate package you have to install in Anaconda. But it's compatible with Sklearn. So once you install Xgboost, the way you interact with it is exactly like the way you interact with any other Sklearn function, and you can use it with Sklearn as if it was an Sklearn function. Okay, so let's see how we designed it then. Okay, so we have a boosted predictor as before, but we now do not have those alpha M's. Okay, and we're going to be designing our base predictors one by one. Okay, so the very first one is straightforward. We just design it to minimize this loss. So imagine this is going to be a tree again in this case. So we just design our first tree, and then we just set our first boosted predictor, or Yeah, the capital F1, we just set that as to the base predictor. Okay. At further iterations, little m, we take previous boosted predictor and then we add the FM that minimizes. Let me put, I think it helps to have this bracket there. Okay. We put the FM that minimizes this big term here. So we have a sum over our samples times the loss. And in the loss, you can see, similar to gradient boosting, we have the previous boosted plus the next, which gives us what would be FM. But we also have a regularization term that's going to help design that tree. Okay, so this is one big difference. We have this regularization phi. Similar to what we saw in gradient boosting, this is too difficult. Nothing's changed. In fact, it's only more difficult because we have this regularization term. So we can't do that exactly. So in gradient boosting, what we did is we settled for a gradient update step of this. In an Xgboost, we're going to go one step further, and we're going to use a second order Taylor series approximation. So we're going to try to, fit it with a quadratic rather than a line. So this is what we do. So we take, this is our ideal loss that we're trying to minimize, and we do a second order Taylor series approximation of this about this point here. So we think of this as the perturbation around this point. So in that second order Taylor series, that means we have the 0th order term, which is the loss at the reference. And then the first term is the gradient of L times the perturbation. So that's this. So G is the gradient, F is the perturbation. Here you can see this is the gradient definition. So this is going to depend on both the step M as well as I, because now we're looking at this non-script L, which depends on a particular sample I. Okay, so this is the gradient term, this is the perturbation. And then we have the second order term in our Taylor series, which is going to be 1/2 times the second derivative, or second derivative here, times the perturbation squared. Okay, so that's essentially our approximation of this term, is this quadratic. Okay, so essentially the thing that we're trying to optimize up here, now we can write it like this. So we have these terms, which are the gradient terms, these terms, second derivative terms, and then we have, it looks like there's a little extra parentheses that we do not need. Okay, so 2 terms in here plus the regularization. Okay, and big brackets around everything. Okay, is everybody with me so far? All right. So now we're going to be specific about our predictor. We're going to assume that all our predictors are decision trees with at most L leaves, capital L leaves. So if you think back to how decisions trees work, essentially what they do is they have a series of steps that takes in an input xi, and it sorts that xi into some bin. So maybe this xi, you make all these decisions, maybe it ended up here and over here. So if it ended up here, remember what we do is we report an output z for that particular leaf L. So let's say this is leaf L here. And in general, L goes from 1 to the total number of leaves, capital L. So this is just leaf L. And so for this, if this sample makes it to that leaf, we output the number ZL, right? That's what trees do. And let's think of this whole, let's give this a name, this process here. Let's give this the name of a function Q that takes in xi. Well, yeah. This whole process of taking in xi and outputting a leaf we'll call Q. And so the final output of the tree is going to be Z sub Q of X. Does that make sense? So the Q is our sorting function, and then we know what leaf it's in, and then we just have a lookup table that outputs Z sub that leaf index. Okay, so Q assigns X to a leaf L from 1 to capital L. ZL, which is a real number, let's say, is predictor output assigned to that particular leaf. Okay, so we're going to focus on exactly this prediction function here. Okay, the next thing to talk about is the regularization. So the regularization that is used takes this form. And I should emphasize, this is a decision tree with a maximum of L leaves. As we'll see, it's possible that some of those capital L leaves will not be used. They'll be kind of left out, but we'll need to say that there's a maximum of L so that when we, let's say, write the sum in this regularization, we can sum all the way up to L. Okay, so the regularization has one part here, which looks like ridge regression, but usually ridge regression, you put it on the parameters of the model. This is actually put on the outputs of the model. It's a little different, but it's a sum of squares, and we have a tunable positive term lambda. And then there's another term which depends on the number of leaves in the tree and some other tunable constant gamma. So these are things we can tune. And we'll see that the role of this is actually to control the number of true leaves on that tree, the number that are being used. Okay, so we're set up. Now we can actually return to our optimization problem here, now that we know the form of F and we can see what happens. Okay, so let's just, okay, so let's plug in for this. We're going to plug in our cost. That gives us this here. We're going to leave out the notation F just to make it a little cleaner. Sorry, the notation M, I meant to say. So there's going to be no more step M, just, this is all happening at step M, so we don't need to write the M. Okay. So we have the regularization. And then, okay, what about this other stuff? So we have GMI. Well, we said we're just going to omit the M so that we write that as GI. And then this is our predictor. Well, if I know which leaf I'm going to, I know that the output of this is just going to be ZL. And then as for the second term, I have 1/2 HI, because we're leaving out the M, and ZL squared. The very last thing is that we need to change the sum, because now we're talking about L instead of I over here. So we're going to break this sum over all the samples I into two sums, a nested sum. The first is all the samples I such that the tree classifies xi into the Lth leaf, and then sum over all possible leaves. Okay, so this is just another more complicated way of writing the full sum over I as a set of two sums. Is that clear? Okay, and that makes it possible to proceed. So now what we can do is we essentially can keep this sum over the leaves L, keep that on the outside, and focus on the inside. So what do we have on the inside? Okay, so we have this term here. Actually, the main thing is to notice that it's a quadratic in Z. So we have a linear term in Z, we have some quadratic terms in Z, and we have a constant term in Z. Okay, so focusing on the Z's then, the linear term we can write this way. So we have a sum over I of GI, and notice that this ZL is not indexed by I, so we can just think of the sum like this, multiplying by ZL. And then in terms of our ZL squared terms, we have two of them. One of them is going to be sum over I times HI, so that's this. And then the other one is just, there's a lambda times that, lambda times ZL. So that's the quadratic term. And then finally, because we're writing this sum here, that sum times gamma gives us gamma L. Okay, so we have just written our costs in a slightly different way, but it's a way that allows us to proceed with our design. Okay, so is everybody with me so far? Almost done? Okay. So how do we optimize over Z? Well, we have a quadratic, so it's actually pretty easy, right? We just take the derivative, set it to 0, solve for Z. So with that quadratic, we end up getting this. So we know how to build that lookup table on our tree. Basically, we build it like this. And in fact, once we've designed ZL like this, we can plug it back in here and here, and we can rearrange those terms, and that gives us the optimization problem over Q, and it looks like this. It simplifies quite a bit. So this is really the optimization of our tree. You know, the hard part of the tree is figuring out how to do all the branches. That's what we're designing now. And you can see that what we have is we have a cost, which is summing over the leaves, and then this is the cost at the Lth leaf. Okay, so the way that we design trees now is the same way that we talked about designing them originally, where we keep splitting. We take our full data, and for the very first split, take our full data. Let's say we talked about subsets of indices. So the first subset of indices has I going from 1 to n, all the data indices. And then we first have to figure out how to split. So we have to choose the feature index, and we have to choose a threshold. And we consider, you know, all the features or some subset of random features, and then we do a sweep over the thresholds, and we figure out the best way of splitting into these two subsets of indices. The way that we talked about it before, we had metrics like Gini impurity, or they were all based on inhomogeneity. That was our guiding principle before. Now, rather than thinking about inhomogeneity, we have an explicit cost. This is what we want to minimize at every time we design a branch. And as you know, once we design this one branch, we just keep repeating that procedure. So then I'll take this subset, this becomes my new samples. I can think about that as S, and then I split that again into S1 and S2, and we just keep going. Of course, we need a stopping rule, right? And we'll see that the stopping rule actually comes naturally in this case. Okay, so, but this is the main thing. The tree can be designed as we described on page 11. Basically, for each one of these splits, we choose a feature j, and then we search for the threshold t that that minimizes our loss. We want to minimize this, and we want this to be minimized after we do the split. We want to minimize that loss on this the new set of subsets. Okay. So that's what we do. So let's do an example. Or let's be a little more specific. So I want to split S into S1 and S2, just like this. So if you think about how much the loss will reduce, this is the loss before the split. So this is the loss before the split. And this is going to be what the loss looks like after the split. So this is what I'm calling the loss reduction. We want the loss to reduce a lot if I do a split, right? That's the whole purpose of splitting, is I'm trying to minimize this loss. And okay, let's look at the ingredients. So if I'm not doing any splitting, I just have my original subset S, then when I sum over I, I'm actually just going to sum over all the samples I. Because at this point, there's no leaves. I haven't even done any splitting. So this like I such that Q equals L, this is actually just sum over all I. So this is what we have before the split. Now, after we do the split, I'm just splitting into two subsets. So there's only two leaves. So I have L is either 1 or L is 2. And I can think about the subsets I such that Q equals 1 or I such that Q equals 2. I can just simply write that as S1 or S2. So this is now going to be, so this guy becomes this for S1 or L equals 1, and then this is what it is for L equals 2. Okay. And now this is where we can finally see the stopping rule come in. Let's say you measure this loss, and you've found the very best feature and the very best threshold for the very best possible split, and now you can measure this. If this is positive, meaning the loss did reduce, that's great. You continue with that split, and then you move on and you consider another one. But if you find that this is negative, meaning the loss actually got higher, meaning in doing the split, things got worse, you say, I'm done. I'm not going to split this any further. That's going to be a leaf of the tree, and I'm going to move on to somewhere else. Okay? So that's the idea. And that is what this regularization term gamma controls. These guys will cancel. But gamma here will affect whether this loss is positive or negative. So it's going to regularize for the depth of the tree. So you can, by choosing gamma, you can choose how deep this tree is. So that's essentially all we can really talk about. There are more details that are like hardware oriented and stuff. If you would like to know more, you can read the original paper. It has a lot of detail in it. But the very last thing then is just to show you an example. So we don't have a demo for this unit, but this is kind of taking the place of a demo. You can find the code if you click on this link. But basically, the main thing I want to show you is how similar this looks to Sklearn. So all this stuff is the standard stuff. You load your packages, you load your data set, you build your feature and target matrices, you do splitting into test and train, And here's where Xgboost comes in. So you have Xgboost classifier. So here's that classifier from the Xgboost package. And then just like you always do with sklearn, you do model.fit on the training data, and you do model.predict on the test data, and that's it. So as you can see here, running Xgboost takes all of 2 lines, just like anything else, and it works really well. You can, if you want to make it work better, there's all sorts of parameters you can tune. And so for the final project, just writing these 2 lines of code and being done is probably not going to win you the contest, probably not going to give you a high score because it doesn't really show much effort or understanding of all the stuff we've talked about with trees. So the better approach would be to try to tune a bunch of those tuning parameters. And we've seen what some of them are. There's going to be gamma, there's lambda, there's L, there's various things you can control. And by tweaking those, you can do a little bit better than the default. Probably not a huge amount better, but you can do a little better, and maybe you'll win the contest. And of course, you're not limited to Xgboost and random forest. There's all kinds of other methods you could try. You've seen we have many ingredients. And in fact, there's a couple methods that are even more recent kind of evolutions of Xgboost. One is called catboost. Trying to remember, but there's other similar things that people are using that might even work a little better. Who knows? You're welcome to try those if you like. But that's essentially all I had for this unit. Are there any last questions on anything? Okay. All right. Well, if not, then my goal, I'm hoping on Friday to be done with the midterms so that I can pass back the midterms here in the lecture as well as go over the solutions. And then next week we can start a new unit. There won't be any homework on this Unit 10. There won't be any lab on Unit 10. There will be a quiz on this unit as well as all the other units. But after this Unit 9 that you're working on this week, no more homework and lab. So you can focus on your project. All right. Have a good one, everyone.